Today we're going to continue our discussion on distributions and how to measure variability. And we're going to distinguish between variability and accuracy. They're two related concepts, but the variability we measure with the standard deviation, and accuracy we measure with standard error. We'll talk about how that all works out. But before we do, this is talking about the COMET trial, very large study, to evaluate progressive addition lenses compared to single vision lenses on progression of juvenile onset myopia. And it's a pretty big sample, 469 kids, and the children were recruited at 4 colleges of optometry. They were randomly assigned to receive either PALs with a +2 add or SVLs. And they were followed for 3 years. The primary outcome measure was progression of myopia as determined by autorefraction after cycloplegia with 2 drops of tropicamide. The secondary outcome measure was change in axial length of the eyes as assessed by A scan. Results were adjusted for important covariance by using multiple linear regression. And what they found was that the 3-year increases in spherical equivalence were -28 in the diopters in the PAL group and -148 in the SVL group. In other words, the single vision lenses were worse than the PALs, progressive addition lenses. The 3-year difference was 0.2 diopters between the two groups, and those differences were statistically significant. Okay. So take a moment and decide if you had a 7-year-old child in your chair with myopia, say -1.5 diopters, who matched the COMET study population, would you prescribe progressive addition lenses? Yes or no? So think about that. You're a doctor. You're going to make a doctor decision here. Treat PALs, SVLs. What are you going to do? Yes or no? Commit right now, yes or no, and hold that thought. We'll come back to this later. In today's talk, we have some keywords that we're going to cover. You'll want to know everything on this list, the meaning of each of these words, phrases. Now, we're talking about measuring variability and accuracy. We saw the standard deviation formula last week. It's the average deviation from the mean, sort of. And then the standard error is computed from the standard deviation. Now, it's computed from it because what the standard error is, it's a hypothetical construct. If you were to infinitely sample your population and compute the mean each time, the variability of the means is the standard error. Now, you can't do that, so you can get a pretty good estimate of what that would be by taking the standard deviation and dividing by the square root of n. So if you look at that, you can kind of tell the larger the sample size, the smaller the standard error. Now let's look at the standard deviation. If you sample more people, are you going to have a smaller standard deviation? Is it also a function of sample size? Well, just like if you took the height of 5 women and averaged them, or the height of 100 women and averaged them, the height of the 100 women wouldn't necessarily be smaller, the variability. So Standard deviation is more of an average, and it's not affected by sample size, whereas standard error is definitely a function of sample size. So let's look at some of the characteristics between standard deviation and standard error. Standard deviation measures variability of the observations. So you get an idea of what's the spread of those observations. Standard error, remember, is the variability of this hypothetical distribution of sample means. So it measures the accuracy of the mean that you have. So it's looking to see, you know, how accurate, what the actual estimate is. If you think about like a survey, and they say plus or minus 5, or plus or minus 10 points, or plus or minus 2 points. The more people that are surveyed, the smaller that plus or minus is going to be, and you'll have a better estimate of what the true mean would be. Standard deviation is based on direct observations, because we take one sample and we calculate the standard deviation. The standard error is a theoretical construct of possible means. We only do one mean, but we estimate what it would be if we did an infinite number of times. The standard deviation describes the variability of the data. The standard error describes the variability of possible sample means of a given sample size. The standard deviation is the average deviation from the sample mean. The standard error is the average deviation from the underlying true mean from an infinite population of possible means. So if you did an infinite number from your population and they were all had an equal chance of being sampled, you would have the mean of that, all those numbers would be the actual true mean. And the average deviation from that's the standard error. Increasing sample size leads to a more accurate estimate of the standard deviation. It doesn't necessarily lead to a smaller one or a bigger one, it's just more accurate. If you look at 100 observations, you're going to have a better idea of what the variability is than if you just look at 5. Increasing sample size always leads to a smaller standard error because it's divided by the square root of n. The standard deviation is directly calculated, whereas the standard error is derived from the standard deviation in sample size. It's not really known. We talk about a 95% prediction interval that encompasses 95% of the observations plus or minus 2 standard deviations. We talk about a 95% confidence interval, which is plus or minus 2 standard errors. Now, the confidence interval is much, much smaller than the prediction interval, because prediction interval is based on the standard deviation and the confidence interval is based on the standard deviation divided by the square root of n. Now, we talked last time about standard score. The z-score is x minus mean. Let's just briefly go over it again. You have an IOP of 15.3 and your sample, or your patient, had a 15.3. The difference is, so you have an IOP of 15.3. You have a patient your patient has an IOP of 15.3. The mean of your normal IOPs is 15.3. The deviation is 0. The standard deviation of x is 3.2. So when you subtract 15.3 from 15.3, you get 0. Divide by the standard deviation and you get 0. So that's our standard score, is 0. If you have an IOP of 21.7 with a mean of 15.3, the deviation is 6.4 divided by 3.2 is 2, a z-score of 2. It's 2 standard deviations. 21.7 is 2 standard deviations away from the mean. If you have a body temperature of 98.8, and as we learned in bad medicine, if the mean is 98.2, then 0.6 is the deviation and 0.3 is the standard deviation. That's 2 standard deviations out from the mean. If your temperature is 100.4, mean still 98.2, 2.6 divided by 0.3, that's a z-score of 8.7. So if you have a temperature of 100.4, that's usually where ERs or doctors say you should come in to the doctor if your temperature is 100.4. Well, that's 8.7 standard deviation or z-scores above the mean. So you're 8.7 standard deviations above the mean. Now let's think about the Snellen chart. So if you're a person with good vision, you have 20/20. If your patient has 20/80, then what is the z-score with respect for that? Well, contrary to popular belief in many articles, you actually cannot calculate that because the Snellen scale is exponential. It is not linear, and so really you should not take the average of 20/20 or other things like that. Instead, you convert the values to logmar, the log of the mean angle of resolution. If you haven't covered that yet, you will. 0 is somebody who has 20/20. The logmar of that is 0. And because 20 divided by 20 is 1, and the log of 1 is 0. If a person is 20/80, that's a log of 0.6. Now in this case, you can figure out from the logmar what the standard deviation is. In this case, it's 0.04. And 0.6 divided by 0.04 is 15 standard deviations away from normal. Now this is why optometry is such a fun profession, because you've got somebody who's 15 standard deviations away from normal. And like if you go to Amigos, person hasn't worn glasses and they end up being 20/80, or even in the clinics sometimes. You have somebody that comes in with 20/80 and you figure out you prescribe them 20/20 or glasses that bring them to 20/20, and now they can see the world. And it is such a huge, huge difference. Remember we said a person can notice a 0.5 standard deviation difference, but this is a 15 standard deviation difference. That's huge, and it's life-changing, and it's why your profession leads you to have such joyous moments. All right, so far we've been talking about single scores, single patient scores, and we have expressed them in units of standard deviations. Well, a standard deviation is a very handy measure of equalizing things. But when we look at studies, then you can apply it there too. So if you take the mean of one group and subtract it from the mean of another group, and you divide by the average standard deviation, that tells you how many standard deviations there are different. And a rule of thumb that we can use, this is, and it needs to be clear, this is not a statistical significance. It is a clinically relevant difference. So if your effect size is a half a standard deviation, then in most cases, this is the minimally clinical relevant difference. In other words, a person can notice a half standard deviation. You don't really notice much less of one. It can still count. You always need to keep track of the difference between clinical significance and statistical significance. We'll talk about statistical significance in the next lecture. Right now, we're talking about clinically relevant differences, and they are two different concepts. Effect size, one thing you need to know, is based on the standard deviation so it is not influenced by sample size. The larger the sample size, the more accurate the estimate is of the effect size. All right, so your question is, or sometimes in a diagnostic situation, you want to know, does your patient belong to the red or the green distribution? The greater the difference, the more likely you are able to accurately assess. Also, if you're looking at a treatment, you have a treatment, might be the green, and is it larger or smaller than the red? So you're looking at the size of that difference. And here, this first distribution, we have an effect size of 0.55 or 0.5. And this is the rule of thumb for minimally clinically relevant difference. And you can see 0.5, not very big. And if you had a diagnostic test, that the difference between the two was 0.5, you would be making a lot of mistakes. If we look at the height of men and women, we can see that the effect size is about 2 standard deviations. So there's much less overlap, but there's still a considerable amount of overlap. We talked about that last time in terms of their height. But 2 standard deviations is a pretty substantial difference in terms of means. Even though individually you could still make lots of mistakes. And if we're looking at refractive error, you can see that there is virtually no overlap between the 2060 and actually I think that was 2080, but that doesn't matter. And so if you see somebody that is 2060 or 2080, you can be pretty sure that they have a problem. So now let's go back to consider the comet question. Here's the rest of the abstract. The conclusions. Use of PALs compared with SVLs slowed the progression of myopia in comet children by a small, statistically significant amount only during the first year. The size of the treatment effect remained similar and significant for the next 2 years. The results provide some support for the comet rationale, that is, the role for defocus in the progression of myopia. The small magnitude of effect, however, does not warrant a change in clinical practice. So if you are going to prescribe PALs based on this study, you are falling prey to the evil god of statistical significance and not of clinical relevance. So the chart, you can see they were both, statistically anyways, adjusted to having the same starting point. And then they both got better, or they both progressed into myopia quite a bit. And this was the difference. This difference compared to this difference is pretty small effective improvement. So even though it was statistically significant, it was not clinically relevant. The difference actually works out to be about 0.2. If you were going to get the minimum of 0.5, the PALs would have to be up looking something like that, which isn't a very big difference either. So let's do some practice examples. At 8 in the morning, what was the effect size of latanoprost improvement from baseline? So these are the times. This is baseline, and this is giving these blood pressure or IOP pressure drugs for 12 weeks. And it started out at 25.7, and at 8 o'clock at week 12, blood pressure or IOP dropped to 17.1. So you would take 25.7, subtract it from 17.1, and then average 2.8 and 3.1, and divide that average standard deviation by this difference. So you should try that. Practice this for these 4 situations on your calculator. You're going to get some more practice in the homework, but just make sure you can understand that. So when we talk about the standard deviation, we are talking about individual observations. There is always variability. Standard deviation says how much. Standard deviation is average deviation. Not all distributions are symmetrical. Prediction interval covers a percentage of observations. That's the definition of this term, prediction interval. And the z-score is a standard score in SD units for a particular patient. Effect size is a standardized difference between means in standard deviation units. An effect size is what's used to determine clinical relevance, whether or not you should go with the treatment or it just gives you that information. Now, the other thing we're going to talk about is measuring the accuracy of our estimate of the mean. So we get a mean, we have a sample, we get a mean, and we want to see how likely we are, or how much variability of that estimate there may be. In other words, if you get a mean of 100, is it right on, or what are the other possible things that it could be? And perhaps even more importantly, though less frequently discussed, is the measuring the accuracy of the difference between means. So you really, when you're doing a study, you want to know what is the difference between means and what is the accuracy of that difference. So we say that the IOP, the average difference was lowering by 10 units. How accurate is that mean, plus or minus what? So we do this with the standard error. When we do a study, we only take one sample to estimate a mean. If we hypothetically took an infinite number of random samples and computed the means, we would get what's called a sampling distribution, as opposed to a sample distribution of observations. The standard deviation of a sampling distribution is called the standard error. Since we only take one random sample, we can only estimate the standard error of the sampling distribution. And so we saw before the standard error is equal to the standard deviation divided by the square root of n. If you have the standard deviation, you can estimate the standard deviation by multiplying the standard error times the square root of n. You need to know this conversion because you're going to want to be able to compute effect size. And people report almost arbitrarily whether it is a standard error or a standard deviation. I mean, you just see it all the time in articles. The standard deviation describes the average variability of the individual observations. The standard error estimates the standard deviation of this hypothetical distribution of means. And the standard error, just repeating this, standard error is used to estimate the accuracy of the mean. So there's this interesting theorem, I guess, in statistics called the central limit theorem. Basically what that means is that if you have a sample size that's large enough, which is an n greater than 30 in symmetrical distributions, the standard error is going to be normally distributed. All statistical tests, parametric tests, the t-test, the analysis of variance, everybody, is based, they're all based on this fundamental theorem, the central limit theorem. And the idea is no matter what the original distribution of observations looks like, the means of random samples from that distribution will be normally distributed. So here we have observations, distribution of observations. It has a mean. It's not quite a symmetrical, it's a little offset. But this part right here is shrunk down here and is that curve. And the sample means are this curve. So the sample means are a lot narrower than the observations. But like I said, the observations don't even have to be symmetrical. So in this case, we have a distribution that we're going to sample from. And the means, the distribution of the means doing this is hypothetical now. This is a hypothetical skewed distribution. This is a hypothetical distribution of sample means. And they are normally distributed. This is important because when we do statistics, we're able to talk about probabilities in terms of this normal distribution, which is kind of a standard thing. And it's really very handy in order to do statistics, calculate p-values and the like. Now we mentioned before we have the prediction interval that's plus or minus 2 approximately, 2 standard deviations. When we talk about means, we talk about a 95% confidence interval. Now this is a somewhat confusing concept maybe because it's based on, again, an infinite number of populations. Okay, so here we have created 20 different samples. They all have exactly the same underlying population mean and standard deviation. And each sample has a mean, and we've calculated a confidence interval, plus or minus 2 times the standard error. And we notice that what is consistent here, or not consistent necessarily, but what is important, that this is the true population mean. And we never know what the true population mean is. But the confidence interval overlaps that true mean 95% of the time. So 1 out of 20, it did not overlap. That is what the confidence interval means. It is how confident are we that our confidence interval overlaps the truth. You can see each time we take a separate sample, we're not going to get the same mean. The mean bounces around. And the intervals aren't even the same. So it's not accurate to say that when you calculate a confidence interval that the true mean falls between the upper and lower confidence intervals. It doesn't mean that, because you can see here the upper and lower confidence intervals are different for every sample. What it means is that your sample can overlap the true mean. It's just kind of a semantic thing, but that's what we're looking at. So one time you're going to miss out of 20, 1 out of 20 you're going to miss, and the rest of the time your confidence interval will overlap. So what it does is it gives you a general, when you get this mean and this confidence interval, it gives you the width of that interval, gives you some idea of how accurate you are, how confident you can be. And it's not so much what the interval actually is as it's how wide it is. If your confidence interval is really wide, then you don't have much confidence that you actually know what the true mean is. If it's narrower, you're a little bit more confident that you're in the neighborhood of the true mean. So, standard deviations offer guidance on the variability of the underlying population. Standard errors inform on the confidence and the accuracy of the sample mean, estimating the underlying population mean. Standard errors also inform on the confidence of the mean difference between means. In other words, we can take the difference between two groups and create a confidence interval around that difference. We need to distinguish between the underlying true population mean, which we don't know, and the observed sample, which we do because we calculate it. Real observations are characterized by the standard deviation, but they're real observations of a sample versus hypothetical distributions, which is SE, and that's an estimate. Journal articles will randomly provide either the SE or the SD, so you must know how to convert one to the other so you can calculate and see how confident you are that there's a real difference, and also calculate the effect size. So, the bottom line when reading an article. There's a couple of points here. This kind of summarize what we've talked about so far. Does the study describe a randomized controlled trial or design that gives you confidence in controlling bias? Does your study have a solid comparison group? Is the sample large enough to give you a reasonable estimate of accuracy with a confidence interval? Does the population sampled apply to your patients? Given the mean and standard deviation of the control or baseline measurement, is your patient within the scope of this sample? Is the relative change in the intervention sufficient to choose this intervention over others? Note, we have not discussed p-values, but we can answer all of the above questions. P-values give us another little piece of information, and we will discuss that next. But realize that p-values do not reflect effect size, do not give you information about how clinically relevant. It's an unfortunate naming that they called statistical significance, using the word significance. But it does not mean that your results are clinically significant. And we'll get into that a little bit more. All right, if you look at the slides, I have some examples that you can go through, and so